Good afternoon, everybody. I'm Mauludi ICOSTA from Physics Department, University of Brawijaya. Thank you very much for giving me time to present our ongoing research regarding band gap control in zinc oxide with sodium chloride adatom density functional theory calculation. Zinc oxide nowadays has very wide application, such as cigarette filter, breakfast cereal, pen pigment, pen coating, piezoelectric, laser diode, light emitting diode, and spintronic. It's also used for optoelectronic application. Actually, now not only zinc oxide but also gallium arsenide. But zinc oxide has a strong point compared to gallium arsenide. It has a high quality zinc bulk single crystal. We see here that for optoelectronic application, the band gap size is crucial. Then people want to be able to control the band gap. Structure of zinc oxide, actually, zinc oxide can exist in three crystal structure: rock salt, zinc blende, and woodside. But the woodside crystalline structure is the most stable crystalline structure. That's why here we use woodside structure. To implement a zinc oxide as semiconductor in electronic device, it has been hindered by lack of control over its electrical conductivity. Actually, if we consider it from the electronic structure point of view, zinc oxide should be naturally p-type semiconductor. But in reality, it's always n-type semiconductor. The cause of this is still under debate. Someone said that it's because of vacancy or other factors. To solve this problem, one needs to control unintentional n-type conductivity to achieve p-type conductivity by giving some treatment. It can be doping or other treatment. Here we use doping, and we choose one from the right side of the periodic table element and other from the left side of zinc and oxygen. So we choose sodium in left side and chlorine from the right side. If we see the electronic configuration, we can see that sodium similar to the zinc. So sodium atom replace the zinc atom in the natrium doped zinc oxide, and chlorine similar to oxygen, then it replace oxygen in chlorine doped zinc oxide. So this figure, we can see the co-doping of um, sodium atom and chlorine atom. Sodium replaces one zinc atom, and chlorine replaces one oxygen atom. This is uh, sodium doped zinc oxide, three sodium atom, and this one chlorine, three chlorine atom doped in zinc oxide. We use a density functional theory. That's why I want to give you a short explanation about this theory. Actually, the real condition is like this for all matter or solid state. Solid state consists of huge electrons which interact each other. So the Schrodinger equation for this system should be very, very complicated or unsolved. You can see this complicated Schrodinger equation because this is actually a many-body problem. So Kohn and Sham simplify this system by mapping to the one-body problem. They consider that this system can be replaced by one electron interact with potential which produced by other all electrons. So it becomes one body problem. That's why the Kohn-Sham equation looks similar to Schrodinger, but much more simple. This is the result for our calculation about band gap. We see here by adding sodium atoms, increase the number of sodium atoms will enhance the band gap. We remember that a sodium atom replaces zinc atom. If we replace zinc atom with sodium atom, it means that we will produce the hole, one hole. Usually, hole, by adding hole, it will induce new impurity state close to the covalence band. So if we see the band gap increase, it means the impurity state is on the valence band. That's why the band gap increase. For adding chlorine atoms, by increase the number of chlorine atoms, we see that the band gap become narrow. So if we see here that we remember that chlorine atom replace oxygen atom. So if we see here, chlorine will give extra electron. So it means it will induce impurity state near to the conduction band. Because here we see that the band gap enhanced, it means that the impurity state below the conduction band. And for co-doping sodium and chloride, we see that the band gap decrease. So it means the influence of chlorine more than sodium. Then we calculated the density of state. We can compare here pure zinc oxide and sodium doped zinc oxide. Here we can see the two p orbitals of sodium atom contribute to the valence and conduction band. And for chlorine doped zinc oxide, 2p and 3p orbitals of chlorine atom contribute to the valence. Conclusion: doping a sodium atom enhances the band gap of zinc oxide, and doping chlorine atom narrow the band gap of zinc oxide. Influence of chlorine atom is relatively more than that of sodium atom, so that for doping natrium chloride narrow the band gap of zinc oxide. Thank you very much for your attention.